Here we're going to be talking about what we call chemical kinetic. So, and now we have more and more to discuss about here today. Now, here we go. When we're talking about chemical kinetic, is the study of the rate of chemical reactions or process. That is just the point there. The study of the rate of chemical reaction process is what refers to as chemical kinetic. So, chemical kinetic governs, from the word kinetic, chemical kinetic governs most of the chemical reactions that take place in chemistry, such as those photocatalysis reactions, autocatalysis reactions, and majority of them like that. This includes the study of what we call the effect of various variables, such as factors to be kept constant at constant this, at constant that, and other physical conditions involved. The arrangement or orientation of molecules on the rate of chemical reactions. Now, in this case, let's talk about this. How much reactant is consumed with what? With times, or how much product is formed with tools. What's called used in chemical kinetic are when it comes to this, what I want you to understand is that the time taken for a particular reaction to proceed, how much reactant is consumed, the product that is formed, and among those tools that we use here include what we call integration, differentiation, and also have what we call inequalities. Okay, these are the tools that we use there. Now, we are going to be using theoretical approach under this particular uh, given topic here. When we say chemical kinetic, in connection to what we call the rate of the reaction. So, how do we calculate the rate of the reaction? Such as being given that, okay, the mass, it can be mass over time taken for those amount of mass to take place. When this is gram, then this one is in seconds, then we have what's called gram per seconds is the unit of that rate of reaction there. And it can even be kilogram consumed per day. And when this occurs, we have what's called kilogram per day, precisely speaking. That is still another point there. But mostly when you deal with what we call the concentration, as far as the concentration is concerned, what you have to know now is that for the concentration, we have this, take note of that. The concentration where we have what's called the mole, when you have mole, then you are going to have the time is going to take. The time is going to take. When mole is m, time is going to take is seconds. So we are going to have what we call mole per seconds. So which is mole per seconds that we have in this place right now. Now, having to look at that, then let us now proceed and begin to discuss about most things we have to talk about here, which include the needed illustration. The needed illustration in this place is the reaction between hydrogen and what we call iodine. Reaction between hydrogen and iodine emphasizes on what happened before and after the reaction, such as the quantity of this used there, used in that place, and the quantity of that from there. In the beginning of the most of this reaction, you realize that we have more of reactant and less of the product. But at the end of the reaction, what happened? We have more of the product and less of the reactant. This also showcases the process involved in a given chemical reaction. So here we go. Here we go right now. Let's discuss more about this. In terms of concentration, which is in form of mole, and in terms of time, which is in form of what? Seconds. There we have the hydrogen, and there we have what's called the iodine. Okay. Now, you see this particular curve you're actually seeing on the board is talking about the reaction that occurs between hydrogen gas and iodine gas to produce what we call the hydrogen iodide. Well, we have H2 reacting together with this to produce what we call HIO2 Okay, now at first, in the beginning of the reaction, what do we notice? We notice that we have more of what we call the reactants in the beginning of the reaction. So as the reaction proceeds, the more of the reactants continue to be less. Yes, the more of the reactants continue to be less, then to produce more of what we call the product that is needed there. And The equation for the reaction that is actually taking place there is given in the form of where we have the equation, we have what we call 1 over 2. Please, we are using differential as one of our tools here, then equals to minus, there we have H2, there we have C equals to minus D, we have I2, then we have what we call dt as the equation involved in such reaction that is taking place. Now, in this place, experimentally speaking, we have what we call the rate equation, which is called rate law. Now, what is the rate equation here? Rate equation is the equation that we're actually seeing in that place. That rate equation then eventually lead to what's called the rate law. Rate law. And how do we express the rate law? The rate, which can be given in form of rate equals to, where we have the Kn, where we have A into brackets, S close bracket, we have B, then raised to power Y. That is the expression for the rate law there. Now, where the Kn represents what we call the rate constant, X is the order of reaction of A, and Y is the order of reaction of B, and eventually the overall of the two of them give rise to what we call the X plus Y, which is equivalent to what? Equivalent to N. So the order of reaction of A is X, the order of reaction of B is what? Is Y. Then the overall of the two of them is X plus Y. We give you what? We give you N. Now, we proceed to what we call integrated rate law. Now, when it comes to integrated rate law, what do we have? Under integrated rate law, from the word integrated, where you should have had the knowledge of what's called integration and differentiation. Okay, we have what we call under integrated rate law, derivation of integrated rate equation, we have number one, zero order reaction. When we say zero order reaction, what do we mean? It's characterized by a non-dependence of the reaction of concentration. What does that mean? Such rate of reaction does not depend on what we call the concentration of the reaction. Such reaction is called what? Zero order reaction. Okay, e.g. cracking or decomposition of NH3 using what we call tungsten as a catalyst. So what is the equation for it? If they ask you to write equation for zero order, there we go. The equation for it now will be rate equals to minus differential of A, then over differential of T, then K0, because the reaction is not dependent of concentration. So the constant here is what is 0. Then we are going to have A raised to power 0 in that case. Since it's now raised to power 0, then we are going to have A, then over differential of A in this form, and eventually give you K differential of T. So if you integrate, what will happen? Then we are going to have the AT followed by what? Followed by the AO. Then we are going to have differential of A, then which will eventually give you this differential of T followed by O. We are going to have KO dt. And when you proceed, we are going to have AT minus AO, AT minus AO, close bracket equals to KO into bracket T minus O. And when you solve what you have in this place, what are you going to have at the end? Now, the product that will be formed there, we are going to have AO minus what? Minus AT equals to, there we are going to have KOT in this case, from what we have here to what we have in this place. So this is equivalent to this one that we have here. Now, this is the final expression for such a given order of reaction. Now, if that is the product, the needed there, then the half-life of a chemical reaction is the time taken for the concentration of the reactant to be reduced by half its inertial volume. So, for the fact that it is the half of the inertial volume, if you could still recall what we call the half-life, under reactive chemistry, then you will realize that from that expression where you have AO followed by AO equals to KO, then T half. T half in this place represents the half-life. We shorten it to what we call the half. Then T half now equals to AO divided by what? 2KO. That is it. That simply means you have to make T half subject of the formula there. And eventually, when you make it subject of the formula, you have what we call this one divided by 2. You have this there. That is what refers to half-life in that place. You can also come across related questions on that as well. And we have some related problems we can use this to solve right now. So what are the related problems that is needed here? The related problem we can use this to solve is given in this place. I'll be using one of the given examples, which is example 1 from the given materials. Okay, derive the expression for the half-life of a zero-order reaction, hence calculate the half-life of a reaction if concentration of the change of 0.1, change of concentration is given to be 0.1 molarity. So 0.1 molarity to what we call 0.025 molarity. Okay, 0.25 molarity after 30 minutes. Now, this occurs after 30 minutes of the reaction. Now, from this question, inertia is given to be 0.1, while the final is given to be 0.25. Take note for the molarity. Now, if you use suitable equation to solve this related problem that we have here right now, then what are we going to have there? I don't mean this is 0. Now, what are we going to have there? Using suitable equation that we have in this place, A naught minus AT equals to KOT. Okay, now what are we going to have here? The inertia is given to be 0.1, then the final is given to be 0.025 equals to, now K naught, the time given from that question, T, which is the T that we have in this place, T is given to be 30 times 60, and that is 180 in that case. So then we are going to have this 1800, close the bracket. Then we solve the mathematics further and see exactly what we have there. When we solve the mathematics of this further, we'll give you 0.076 equals to K naught 1800. Dividing both sides, we have K naught equals to 0.076 divided by 1800. And what would that eventually give us? That will give us 0.0. That will give you 4.22 times 10 raised to the power what? -5 mole per second as the final answer there. So if this gives us this as the final answer that we have in this place, then since we need to calculate the half-life, according to the question asks us to calculate the half-life. So the half-life now will be, remember the previous formula that I gave you, half-life is T half equals to, well, we are going to have A naught over 2KO. And our A naught is given to the what? 0.1. That is 0.1 over 2 times. Our K is 4.22 times 10 raised to the power -5. So eventually, what are we going to have over this? 8.44 times 10 raised to the power -5 will eventually give us 1.18 times 10 raised to the power 3 seconds. That is exactly what we have there. So this is way of calculating what's called the half-life, okay, under a given expression of this type. Now, let's talk about this further. There are many related problems we can be asked to solve there. So this is the one of them that I have solved right now. Now I proceed to the next part, which has to do with, we have checked what we call the zero order. Now let's talk about the first order reactions. When it comes to first order reaction, there is also an expression for it as well. Take note of that. There is also expression for it as well. First order reactions. Now, when it comes to first order reactions, a first order reaction is one in which the rate of reaction is proportional to the concentration of the reaction raised by the power of unity. Take note in this place, the rate of reaction is proportional to the what? To the concentration of the reaction. Is proportional to the concentration of the reaction. That's just that then. So in this case, rate of reaction is proportional to concentration of the reaction, is proportional to it. Now, since it's proportional to the concentration of the reaction raised to power unity, now we have a way of expressing what we call the first order, and it's not the same way we express the first order. We are going to express the second order and third order of a given reaction. So how do we express the first order of a given chemical reaction? This is how we express it. The rate is given in form of where we have A equals to the what? Equals to the product. So if A is equal to the product from what we have here, then we can have it at rate equals to, we are going to have differential of A, then over differential of T equals to K, then we have this. Not like the previous one, which is raised to power 0. So this is not raised to power 0 this time around. Then we have minus A into bracket, where we have A here equals to, then we have the T. Then if you differentiate 18, we have AO minus D, A, close bracket, A equals to STO. Then we are going to have K dt. We have differentiated this. We have integrated this. We have integrated this one that we have here. So after the integration, we introduce what we call the constant proportionality, where we have the ln, then A. We are going to have ATAO equals to KI close brackets C and O. Now, then from there, that will now lead us to where we are going to have ln AT, just like the way we have done the previous one, the ln AT minus ln AO close bracket equals to K1 into bracket C minus O. Now, from what you have here, the two of them have ln in common with the negative sign, and we are going to have ln, followed by AT over what? Over AO, eventually minus what? K, then we have T there. So finally, finally we are going to have 80 now. 80 now equals to AO exponential of K, then T there. So using what we call the linearized form, this is not linearized form. Using what we call the linearized form, we are going to have ln 80 over AO, then we are going to have equals to minus K plus C. That's plus TO. Now, where is this actually coming from? Where is this actually coming from? Remember linear equation. Which linear equation? The equation of y equals to mx plus c. So everything here is equals to minus k1t plus 0. So y equals to mx plus what? Plus c. That is the exact expression that we have there. So that's why we call it linearized. Take note of that. When you write it in linear form, that is the expression that is going to give us there. Now, from the expression that we have in this place, we can use the graphical forms. We just continue to write it further. We also have what's called the half-life expression of this one here. If we use the half-life, we can also arrive at a safer final answer there. But for the half-life, I will just give you, I won't write the half-life. I will just give you what we call the equation of the half-life. And the equation of the half-life is given in the form. The equation of the half-life is given in the form half-life of first order. First order. So the half-life of first order now will be where we are going to have half equals to 0.639 divided by k. So we all know what our k represented, which represents our what? Our constant. Now that is it. Now let's look into this carefully. We have one given example that we are going to check here right now. Now the example given in this place asks us to calculate something that is very, very essential. The sample given here is that, given that for a first order reaction, the concentration of the reactant changes from 0.1 to 0.0025. Change in concentration, which is 0.1 to what? 0.0025 molarity. Okay? In what? In 60 minutes. In 60 minutes time. Now, the question asks is calculate the rate of reaction. Number one, rate of reaction. And number two, the question says, okay, rate of reaction when the concentration of A is 0.05 molarity. When A equals to 0.05 molarity. And second one says half-life of the reaction. Half-life of the reaction. Half-life of the reaction. Now, with respect to that, we are going to start with the first question that we have there. So in this case, we have to analyze, of course, what does the question ask us to do? The question asks us to calculate the rate of reaction. So in order to calculate the rate of reaction, which formula will be suitable for this? First of all, inertial concentration is given to be 0.1, and which represents our, A naught. Our final concentration represents 0.0025, which is our 80 there. You know that one. Then the time taken, which is what? The time taken in seconds. We're given 60 what? 60 minutes. 60 times 60 will give you 3600 seconds. Now we are going to go to solve this problem. So what do we do next? Just take it to the next step forward. Using the formula. Using the formula where we are going to have ln of AT over A naught close bracket equals to minus KT. That's the formula we are using here. So what is our AT? Our AT ln of our AT 0.0025. Then our A naught is what? 0.1 equals to, remember we are looking for K, then multiply by the time. The time taken is what? 3600. Okay. Now, from what we have here, when you use this to divide this, then ln is going to give you 0.025 equals to minus K, then times 3600. Now, you proceed. From what you have here, look for the ln of 0.025. The ln of 0.025 will give you minus, that should be 3862 equals to minus K times 3600. Okay, now what next? Do the mathematics. The mathematics you just have to do here now is to what? Make a subject minus K equals to, dividing both side by this. That should be, now, minus K. Please take note of this carefully. Take note of this carefully. Take note of this carefully. What's that? This is minus, this is also minus. When minus go to the other side, it becomes, let's say by dividing, minus 1.3862 equals to minus K times 3600, dividing both sides by 3600, 3600. This cancel this, this cancel this. This leave behind negative. So when you eventually, negative will eventually cancel the negative, leaving behind K equals to, we are going to have 3.85 times 10 raised to power minus 4 per seconds. That is the answer to the question. That's what the question asks us to calculate here. So K equals to exactly what we have in this place. That is what the question asks you to calculate. Now, secondly, the question asks you to calculate the half-life. So how do you calculate the half-life? In order to calculate the half-life, recall the formula that I gave you for calculating half-life earlier. I said half-life, C1/2 equals to 0.639 divided by what? Divided by K. Now, in accordance to that formula that we have there, the K from this place, now, as far as the first order is concerned, you have to be specific with what the question is talking about. You are given A when it changed from what? 0.05. Okay, 0.05 molarity. Please, the question asks you to calculate rate and not the constant. Pardon me for that. So since when our A is now at 0.05, recall rate R equals to K, then into bracket what? A. So our K now have been calculated to be 3.85 times 10 raised to power minus 4 times when our I is 0.05. Then what are we going to do? Use 6 to multiply this. What they have at the end. You are going to have the final answer of R to be 1.925 times 10 raised to power minus 5 rates mole per seconds. So that is what the question asks you to calculate for number 1. This is just your K. So R equals to K into bracket A. Take note of that. So for number 2, which is half-life, our half-life now will be in the forms of T half equals to 0.639 divided by, now what is the value of our K? The value of our K is what we have there, 3.85 times 10 raised to power minus 5. Then when you use this to divide, what would that give you at the end? The end will be 1.8 times 10 raised to power 3 seconds. That's what we're going to have at the end. That is the next thing that the question asks you to calculate there right now. So that's number 2, using the formula that you have in this place. So recall that the formula is T half equals to 0.639, all divided by what? Divided by the value of K. That is exactly the formula that we use to solve this problem here. Okay. Now, there are many problems we can use that to solve there, as far as we have the necessary parameters, available. So that is that about that there. We shall be looking at some related exercises, but before we look at the related exercises, this is first order. Let's talk about the second order. Second order of reaction. Second order of reaction. For second order of reaction, okay, we just have calculations to solve in this place. Precisely speaking, of course, we have calculations to do here. No much derivation because this time around it's getting complex. So for the second order of reaction, we're asked to consider the following reaction, and we're asked to calculate one or two related problem underneath. So that is what I'll be using to explain what's called the second order of reaction in this case. Before I go into the second order of reaction, I would like us to check this expression together because there's tendency that you can come across a related problem to it. The activation energy can be calculated. When a question asks you to actually calculate what we call activation energy from a given parameters, then thinking of what should be done there precisely speaking. I just quickly found this right now, and I must be sincere with you that we have to work on it carefully, precisely speaking. There we go. The question here now says, before I move into the order that we have there, to discuss about, okay? So before I move to the second order, let's check this problem together. The question says, for a particular first order reaction at a 300 Kelvin, the concentration of reactant is reduced to 1/2 of its inertial value after 5,000 seconds. At 310 Kelvin, the concentration is halved after 1,000 seconds. So the question now says calculate the rate constant for the reaction at a 300K and 310K. And the Roman figure 2 says we asked to calculate the time required. The time required for the concentration to be reduced to 1/4 1/4 of its inertia value at 300K. Aroma figure 3. So if you check your course materials, we definitely see something like this there. Aroma figure 3 says the activation energy of the reaction. The activation energy of the reaction. So these are the things we are going to be checking together right now. Now, we need to focus more of our attention on solving this given related problem. Now, in order to solve this problem, what are the givens that we need in this question? You have to check it out. What is that? You have to calculate the rate of the reaction at what 300K and 310K. And at first, you have to understand that in this case, we have the concentration is half as what? At 1000 seconds. Okay. So in this case now, this is what I want us to understand carefully. The initial temperature and final temperature have to be treated carefully. And also the initial time and final time have to be treated carefully. So let's move closer and see how this problem is being solved. So for the first question, what the first question asks you to calculate there, you need to calculate the K, which is the constant that is needed. Okay, constant at different what's it called? The constant at different temperature. Okay, let's go there. So using K equals to 0.0. Remember that half equals to what? Equals to 0.69. I mean 0.693 divided by this divided by K. So we are now making K subject of the formula now. So what will happen? It will now become K equals to 0.693 divided by what? Divided by half. That is what we're actually doing here. So K in this place now will be K at 300 Kelvin of the temperature when T half equals to what? Equals to 5,000 seconds. So here we go. Then K equals to 0.693 divided by what? 5,000. And that will give you what we call 1.39 times 10 raised to the power minus 4 seconds. That's one there. You calculate for the second one. Second one, K at 310. Then when Kelvin, when our T half equals to 1,000 seconds. 1,000 seconds. So what do we have there? What we are going to have there is K equals to 0.693 divided by 1,000, and that will give you what? We are going to have 6.93 times 10 raised to the power minus 4 per seconds. That's the second one that we have there. So we've obtained the K for the two of them. So from the equation, pardon me to take this off. So from the equation, we have it as ln of what we call the final over the inertia equals to what? Minus K, then followed by T there. So that means in this place, our AT, they said when it is now reduced to what? To 1/4. Okay, for it to have been reduced to 1/4, which means that we are going to have our AT now. Our AT now will now be over 4. Yes, because our AT is already 1/4, which is equal to this. That is times AO. So which is now AO over what? Over 4. That is what it means. So at 300K, what do we have for it? At 300K, this is what we have there. For K1, we are going to have, for K1, which is given to be final answer of 1.39, with respect to the values that we have there. What are we going to use? We use our lane straight up. Then our lane, we are going to have over 4, then equals to minus 1.39 times 10 raised to the power 4. We are looking for t in that place. That is multiplied by t. So when you multiply it by t, what would that give you? Now, that will eventually give you this. The lane of wherever that you have in that place will lead it to minus 1.386 equals to minus 1.3 minus 1.39 times 10 raised to the power 4, then times t. So divide both sides, what we got eventually gives you. Then we are going to have our t equals to 9.97 times 10 raised to the power 3 seconds. T is equivalent to that there. So that is what that question asks you to calculate in that place for the first question there. Okay, since you have obtained that, the question asks you to calculate the rate constant for the reaction at 300 and reaction at. So the 300 rate constant at 300 is this. Rate constant at 310 is this. That we have there. The time required for the concentration to, to go down. The time required, which is Roman figure 2, is this one that we have there. The time required, or number 2. This is the one that we have there. The time required is 9.97 times 10 raised to the power 3. Now, Roman figure 3 now says the activation energy of the reaction. So to calculate activation energy, there's a specific formula that we use to calculate the activation energy. We don't just calculate. The activation energy in this place is that we are using this formula. Ln K2 over K1 equals to our activation energy EA over rates, then into brackets where we are going to have 1 over T1 minus 1 over T2. That is exactly what we are actually using here. This is the exact formula we are using to solve the problem. So T1 and T2, of course, T1 is temperature 1, T2 is temperature 2. Of course, we've already have everything that we need available. So what are the things that we need? The parameters we need here is our K1. So what is our K1? Our K1 is 0.000139. Recall from the one we calculated before. Our K2 equals to what? 0.000693. Then our R is always 8.314. You still remember this? Our R, that's molar constant. Then our T1 equals to 300 and our T2 equals to what? 310. Now, for all of them that we have in this place, let us compute all these parameters together and see what we have. Ln K2 is what? 0.000693 over K1 is what? 0.000139, then equals to EA over activation energy over R, which is 8.314. Then close brackets 1 over our T1 is what? 300 minus our T2 is what? 1 over 310. That is the expression. This expression that we are in this place is the one we want to use to calculate the what? The activation energy. Now, from what you have in that place, we will compute all of them from A to Z. Very, very essential. Just continue the arithmetic. So, remember, I'm solving problem number 3, 1, 2, 3. That's the problem I'm actually solving right now. So, the next thing you are going to do here, using this to divide this, what are you going to have? The ln of that division will eventually give you 4.9856 close bracket equals to our activation energy over what we call 8.314. Meanwhile, the mathematics of these two is that we inverse them, and when we inverse them, something will happen there. What would that? We're going to have 310 minus 300, and eventually we are going to have 300 times 310. In that case, that's what we are going to have there. So that is what will happen. So from that place, what next? The lane will eventually give you lane of this value that we have here. We give you 1.66 1.6066 equals to the activation energy over 8.314. Now into brackets, subtract this from this, use this to divide it. What would that give you? That will eventually give you 0.000108. That's it. That's exactly what you must have then. Take notes. Take away 300 from this will give you 10. Then use this to multiply this. 10 divided by whatever you have here will give you this one here. Now, you still have to continue with the mathematics. The mathematics in this place now is quite simple to see that. This will come here. We give you 1.6066 times 8.314. That is, you cross multiply. This will go here. This will go here, like this. Then equals to EA. Then we are going to have 0.000108. Close the brackets there. Now, when you multiply everything that you have here, this will give you 13.3572, all divided by this one is 0.000108. Everything equivalent to what? EA. And when that is equivalent to EA, then when you use this to divide this, what would that give you at the end? That will eventually give you 123678. 123678 equals to EA, that is activation energy. Implies that our activation energy is now equals to 123678 joule per mole. If we convert this joule per mole into what we call kilojoule, that means we divide it by 1000, and that will eventually give you 12 points. Okay, that is 123.678 kilojoule per mole. That is our final answer to that question there. So the calculation that we are actually seeing in this place is inside the past question. Yes, that's why I have to quickly solve it, because I could remember I came across something like this. So it's definitely inside the past question. So whenever you come across the problem, this is how the problem is being solved there. So next class we are going to be looking at what we call the third order. Yes, second order and third order. That is what we are going to check on our next class. Thank you.